it's fine. Okay. Hello. Okay. So any question from this side? If you don't have question, but you actually should have question because I actually made a mistake when I was doing the solution. Okay. So problem 5 is actually pretty hard to compute, and this shows why computational space is important in doing calculation, because if you don't have enough space, then you will miss I have an I here I didn't see. Okay. So I forgot to multiply this I when I was calculating this y minus and 0 order product state, and so this whole term should actually equal to 1 over 2, and that is I minus 1, 0, 0, 0. Okay. And so this thing is actually now this. It's actually so I plus I dagger equal 0, and this is minus 1, this is plus 1. And so this thing, okay, so this is actually still 1.5 because I made a mistake. And it should be, sorry. So this is minus 1, and I make this wrong again. Okay. So I made more mistake here. Okay, so y minus is actually 1 minus I, right? Okay, y minus I here. Okay. So it's I times minus I here, and this is actually plus 1 here. Okay. So this is plus 1, and and we say this thing is this thing dagger, so it's a minus I and also plus 1 here. So this matrix here is actually, okay, maybe let me just erase this thing, easier to make it less confusing. So this whole thing here is 1 over 2. 0, 1, 1, 0, I believe. And so the end result here is this whole thing, and it's minus I plus 1 over 2 here, and I plus 1 over 2 here. Okay, so little errata on the midterm solution. Okay, is that correct? And okay, so maybe in a less conjective way, so it's 1 over 2, 3, 1, 1 minus I, 1 plus I. And then we need to divide by another 1 over 2, we say, so the actual answer is 1 over 4, this thing. So you have trace 1. Okay? Hopefully I'm doing this correctly now, and let's have another one similar in the homework to make sure everyone got it. Okay. Anyway, that's midterm, and that's back to actual teaching. Okay. So actual teaching, let's go back to quantum algorithms. So we talk about a lot of quantum algorithms. They are all query algorithms. Okay. And so we see that we have this Dirichlet's algorithm that says you can do. You can solve with one quantum query, but need to solve with two classical query. Then we have Dirichlet's algorithm. That says you can solve one quantum query and say solve with with a constant randomized classical query, or 2 to n over 2 determinist classical query. And then with Bernstein versus Ronnie, you have this 1 versus n and Simon's algorithm. That has order n quantum query, but order 2 to the n over 2 classical query. Okay? So we see good separation in those query algorithms. But now we want to see, maybe we want the exponential separation in practical quadrant. And here we have a practical quadrant that's factoring. Okay, so we are now going into the famous Schwartz algorithm. That we will see an exponential speed up between quantum and the classical algorithm. Okay, and but this is the factoring is actually not a query problem, although we have been talking about query problems. So factoring is it's a bit complicated, but factoring by itself is not a query problem. It's you give a number and you are going to find two factors. Okay, but we will see that we can kind of think some part of it as a query algorithm. Okay. But anyway, it's a non-query algorithm, so this exponential speedup is a bit weird because we have a very fast quantum algorithm, but we cannot really prove the classical algorithm is slow. Okay. So we don't know if it's classical algorithm, but in practice it's an exponential speedup. Okay. But anyway, let's go into see how we do Shor's algorithm. But Shor's algorithm is very complicated. It has a lot of different components. And now we go into the probably the core part of the Shor's algorithm is a technique called quantum Fourier transform. So it's a quantum algorithm for doing Fourier transform. But people are probably not too familiar with Fourier transform, so let's first talk about what's a Fourier transform. So Fourier transform, now we are talking about this basically classically, okay? So here, this is basically classical discrete Fourier transform. So we are thinking about, okay? So we stop thinking about quantum for a while now, okay? So for like 3 slides. And for now, we are just thinking about classical information processing. So we have a vector of whatever classical data, okay? So it's an n-dimensional vector, x0 to xn minus 1. And there is this Fourier transform thing that people like to do a lot. That will transform this x0 to xn minus 1 vector to another vector that's y0 to yn minus 1. And it's basically a linear transformation that's done by multiplying this Fourier transform matrix. Okay. And so y is just f times x. Okay. And f is this matrix. Okay, so f sub n because for every dimensional n you have a different f. Okay, and f sub n we just write this matrix element here. So f sub n of kj is this interesting thing. So it's 1 over square root n. It's just a normalization vector, and this phase vector e to 2 pi I jk. So jk is this kj here, and then we are tying over basically this phase vector of e to 2 pi I divided by n. So it's the nth root of 1. Okay. So you can also think of this as 1 over square root n and omega to the kj. Okay. And so for some example of f up here, so f2 is okay. So n equal to 2. So 1 over square root 2. And okay, omega here, we have e to 2 pi divided by 2. So omega equal omega, okay. So I should say omega sub n, okay. Because omega also depends on n. Okay. Omega sub n. And omega sub n here is minus 1. Okay. So you have minus 1 to a 0, 0 equal to 1. And you have minus 1 to the 0 times 1 is still 0. Okay, so minus 1 to, so for example, this one is minus 1 to the 0 times 1. Okay, because of kj. Okay. And and this one is minus 1 to the 1 times 1, and that's minus 1 to the 1, that's minus 1. Okay, and so that's f2, then you have f3. So so it's like this. So now the omega is weird e to 2 pi over 3. Then you have 1, 1, 1. Because here, I know which one is kj. So probably j. So this j equals 0. J equals 0, so jk always equals 0. So you just have omega to a 0 is going to be 1. Yeah. And on this column, you have j equal to 1 and k equal to 1, 2, 3. Kj. I'm writing kj. Okay, so j is this one. Okay, and so j equal to 1 and k equal to 1, 2, 3, and so you just have omega to a 0. Sorry, not 1, 2, 3, 0, 1, 2. So j equal to 1 and k equal to 0, 1, 2. So it's omega to a 0, omega to a 1, and omega to a 2. and then j equal to 2, then you have this 1 omega square omega. And then this one here you have, okay, so this is omega 3. And here we have omega 4. Okay. Omega 4 is I. So it's the fourth root of identity. Because I squared equal to -1 and minus squared become 1. Okay. And yeah, so similarly, the first row, first column are all 1. Then it's 1 omega squared, omega 4th. And 1 omega 2 omega 4 omega 6 equal to omega 2, etc. Okay. So yeah, so like this is omega to the 3, and this is omega to the 6 equal to omega 2, and this is omega to the 6 plus 3, so 9 equal to omega, etc. Okay, so that's F. Okay. And so some digression. So we say this is a classical thing, it's a classical Fourier transform, but our notation is funny. So so if you compare to actual classical Fourier transform, this is actually inverse Fourier transform. Okay. Okay. So we are having a little different notation to actual classical literature. But anyway, this is some matrix we can define, and in this class we call it Fourier transform. Okay, so yeah, so this is how this transform is defined. So y equal to f of x. So y vector equal to this f matrix times x vector. Okay, and okay, so we are going a little back and forth, and so well, this is the definition now. So we can kind of stop now, but let's also, okay, so let's see, and let's also see some example of it. Okay, okay, and so for example, if you put, say this example is easier. Okay, so say if your x vector is this kind of a standard basis vector 0, 1, 0, 0, 0, 0, 0. And then you see what's the y here, and then you see that this thing will basically pick out the second column of your F matrix, and that will be this 1 omega square all the way to omega minus 1 vector. Okay, and yeah, so you can see that this Fourier transform give you superposition of those alternating omega vectors. Okay, and then an interesting example is this. Okay, so you put O1 vector into your Fourier transform. Now you have a superposition of all those weird omega to the n vectors, okay, or omega to the k vector, and these alternating omega vectors. And it actually turns out this become 1y squared and 0, 0, 0, 0, 0, 0. Okay, and this thing can be verified by this formula here. This is very important. You need to remember this is the basis of a lot of the Fourier transform calculation. Is basically a orthogonality between those columns. Okay, and okay. So what does this say? Okay. So let's check how this O1 vector got Fourier transformed. Okay, so O1 vector. And maybe let's go to formula. Okay, so I should actually say this first. Okay, so so think about y vector is f and times your x vector. Then you think about what's the case element of I. Okay, so yk is just so you do this matrix multiplication. So yk is fn of kj, and is sum j, fkj xj. So this is how this is how matrix multiplication actually works, right? So yk is, yeah, because you write down elements. So the vector out of fn times x is element is So the case element is fkj times xj summing over j. Okay. And anyway, so this is the basic matrix indexings. So because y equal to f times x, so yk equal to f sub kj times xj summing over j. And anyway, then we can go over things. So we have xj here and fkj we have here. So yeah, so yk should equal this thing. We're just taking out this 1 over square root n because it doesn't depend on j. Okay. So yj is 1 over square root n sum over j, xj, then is omega n to the kj part. Okay. So e to the 2 pi jk over n. Okay. And okay. And then okay, so now let's see what this yk is if our xj is all equal to 1. So if we don't have this term here, basically, so it's just 1 over square root n summing over this e to the 2 pi jk over n. Okay. And okay, so when so obviously it depends on k, and so when k equal to 0, okay, so this thing is 1 over square root n sum over this thing. And so basically we want to study what's this thing, right? So sum over j and e to the 2 pi jk over n. Okay? And this thing, well, it's easy when so it's a function of k, and j is a dummy variable, j is going to be summed over. So k equal to 0, this is easy because if k equals 0, then the exponent is going to be 0 always, and e to the 0 is just 1, so you are summing over a whole bunch of 1. So the summation is just going to be equal to n when k equals 0. Okay. So like we say here, so when k equals 0, you have a summation j from 0 to actually n minus 1. Okay. J from 0 to n minus 1, and this e to something is always 1, so that's just n. Okay. Okay. So, okay, then n divided by square root n is square root n, so that's why we get a square root n here. And all other terms are 0, and that's because of this fact. Okay? So we say when k not equal to 0, then you sum over j, then these things are going to be equal to 0. Okay? And you can prove this rigorously mathematically, but I'd like to get intuitive proof here. Okay? So intuitive proof is that if you sum over j and you think about how those things look on complex plane, it's going to be evenly spaced out points on a circle. Okay? So for example, we have n equal to 5 example here, and n equal to 5, and we have omega. Okay, so n equal to 5, and we have 5 points here. So this omega equal to a 0 over 5. So it is omega 1, omega to a 1, omega to a 2, omega to a 3, and omega to a 4, and omega to a 5. Okay. Okay, so this point is omega. And okay. And so let's say k equal to 1, right? When k equal to 1, what points are what you're summing over? K equal to 1 and j equal to 0. So k equal to 1, then j equal to 0 is obviously here, because it's e to the 0 always. Okay? And then j equal to 1 is going to be here, is k equal to 1. So j equal to 1, then you have omega. Okay? So this is omega n to a jk. Right? So k equal to 1, then the j is just going to through these points one by one, right? So j equal to 1, you have omega to a 1, and then j equal to 2, and then you have j equal to 3, and j equal to 4. Right? Okay, so those are 5 points you sum over, so you'll see you are summing over those 5 points exactly. And then you can kind of convince yourself because of you have these points are evenly spaced out through this circle. So when you sum over them as a complex number, it's like you sum over then as a two-dimensional vector, and you can intuitively they should sum equal to the 0 vector, which is just 0 here. Okay. Okay, so that's okay. So that's k equal to 1, and what about k equal to 2? Okay. So maybe let's do the erase here. That's over. Okay. So k equal to 2. Let's do this slowly. So k equal to 2. Then j equal to 0 is still this point. And j equal to 2. Then kj not equal to 2. And sorry, j equal to 1, kj equal to 2, right? So j equal to 2 here. And sorry, j equal to 1. jk equal to 2. Okay. So 0, then j equal to 0, and j equal to 1 here. So each time you will progress 2 blocks, right? Because k equal to 2. And so j equal to 2, it should go 1, 2, and it should go here, right? J equal to 2, and kj equal to 4, so 1, 2, 3, 4, as we expected. Okay. So j equal to 2, and j equal to 3 is here. And j equal to 4, then you see it's here, and then you see you are still over those 5 points, right? And yeah, and maybe let's do one more, and k equal to 3, and so j equal to 1 will be here, then 1, 2, 3. J equal to 2 will be here, then 1, 2, 3, j equal to 3 is here, then 1, 2, 3, j equal to 4 is here. Okay. So you see, it's always evenly spaced out points on a circle, and that's why they all always sound equal to 0. Okay. And okay, so that's the next example. Because so this is not quite a proof, but this gives you some idea. And I guess to confuse you a little bit, so n equal to 5, so 5 is a prime number, so it's always those 5 points. But you have n equal to 4, then it's a little weirder, right? So if n equal to 4, then the omegas are those 4 points on complex plane. So 0, I, -1, and I. And say you have a j equal to 2, sorry, k equal to 2. K equal to 2. Then you are going to jump between those 2 points. So you have a j equal to, and okay, so the usual power macros of age stuff. Then anyway, so you are going to jump between those 2 points. So j equal to 0 will be here, and the j equal to 2 will be here. Then j equal to 3. Sorry, j equal to 0, j equal to 1, and j equal to 2, j equal to 3. Okay, and yeah, so it's this whole column. So 1 -1, 1 -1, and then some equal to 0. Okay, and okay, we are back. So this point will be j equal to 0, 2, and this is j equal to 1, 3. And anyway, so those things, so 1 plus -1 plus 1 plus -1 is equal to 0. Okay. So sometimes they don't go over all points if this n is not a prime, but they still sum together to 0. Okay. And yeah, so this is a nice relationship to remember. This is e to the 2 pi jk. Yeah. This is e to the 2 pi jk sum over j equal to 0. Okay. Question so far? This is, I guess. Okay. So, any question about this calculation? No. Then okay. So let's talk a little more about the interpretation of Fourier transform. Okay. So Fourier transform, we like to think this as a transformation between time domain and the frequency domain. Okay. So time domain, we are thinking we have, okay. So this way is actually f, and this way is f minus 1 because our f is is reverse ordering. So because we are defining f as the inverse Fourier transform. But anyway, so we have some thinking between transformation between time domain and the frequency domain. So we think about in time domain our signal is some sinusoidal signal or exponential. So we think you have e to the I omega t here. Okay, and okay, so sinusoidal function is kind of like a complex exponential. Yeah, or as you say, complex exponential is kind of like a sinusoidal. Okay. And so Fourier transform will say that we want to decompose our function into summation of complex exponentials, and the coefficient to the complex exponential is whatever you should write in entanglement. Okay. So we are saying if we have okay, actually we are defining f this way. Okay, so it's like saying we have a signal with frequency 1 here, and with only frequency on the 1 here, and we transform to a time domain, it will be like a sinusoidal function with frequency 1. Okay. And you have a frequency 0 function here, and we should transform to a constant function. And you have a frequency higher function, and we should transform to a higher frequency function, etc. And as we say, this sinusoidal we think is like a complex exponential, because complex exponential is cosine theta plus sine theta. Okay, so this is a very quick intuition. So I guess this one, okay. So this one to this thing here is the example here. Okay. And so this example, in terms of the picture here, we are doing something really funny. We're actually saying that if you have so we're actually saying if you have a constant function, so if you have a spike function on your time domain, then because we are discrete, then it's actually equal to you have a constant function on the frequency domain. Okay. And okay, so it actually should not be 0 to n, so it should be 0 to n minus 1, because we only have n things. 0 to n minus 1, n minus 1, n minus 1, n minus 1, something like this. Okay. Wait. Should I? 1, 2. I guess we didn't. Or if I write it this way, I guess I should really write it here. Doesn't really matter, but yeah, because it's one period. Okay, never mind. Anyway, that's very quick introduction to classical Fourier transform for discrete, discrete function or a discrete set. So any question for now? Yeah. Once again, so the basic definition we have a Fourier transform is just this matrix. You want to transform an n-dimensional vector to its Fourier transform another vector, then you just multiply this matrix. That's 1 over n e to the 2 pi jk divided by n. So it's nth root of 1 times 2 to the jk and times omega n. That's a kj's element. And a nice expression for the kth component of your output vector is 1 over n, then summation j xj e to the 2 pi I jk over n. Okay, and yeah, so this is the formula, and we have whole sort of interpretation. Okay, and okay, so one thing you can show, okay, so I think this is actually same as the other homework, but one thing you can show is that then you can do inverse Fourier transform. Okay. So inverse Fourier transform is actually very similar to Fourier transform. So it's another matrix, and basically with the same matrix element, but you have the fn to the kj or jk is still e to the 2 pi jk, but with a minus sign here, and the 1 must square that. And because this inverse Fourier transform exists, that's why we can kind of make sense of those frequency domain and time domain thing, because you think your signal is a vector, this whole vector as a signal, you transform it to another domain, then you can just transform it back. So those two things, we are thinking those this x vector and this y vector are containing same information. You are just doing some linear transformation on them, so it's like you are doing a changeable basis. Okay. And yeah. So this f is the inverse, and actually we are going to see f is a unitary too. So really we are just doing a changeable basis to represent those two vectors. Okay. So that's classical Fourier transform, and you probably heard its name already a lot, and it has a lot of applications. And now, yeah, it has a lot of application in analyzing your signal or processing your signal. But now back to quantum algorithm. So that's the end of talking about classical information processing. Now back to quantum algorithm. Now we want to ask whether there is a phase quantum algorithm to do Fourier transform. Okay, and okay. So now we go to quantum Fourier transform. It's something really fast, but we are doing something funny. Okay, so now so remember classical Fourier transform was saying this is a vector of classical data. Okay, so now we do quantum Fourier transform. We just are thinking this vector as a quantum state. So now we have some restriction on this vector, because the classical data, those x0 to x1 and -1, they can be anything. It can be any complex number. But now this is a quantum state, so now this x vector and the y vector are quantum states, so they need to be normalized. Okay. So now x and y are univector. Okay. And okay. And now we think, can we have now this y vector as fn times x, okay, with fn as the discrete Fourier transform matrix we defined before. And okay, so for this to make sense as a quantum transform, the first thing is something you need to show in homework. Okay, so you need to show fn is unitary, because we said that x and y need to be both univector. But x, if we fix x as a univector and fn is already fixed, then y is already fixed. Okay, so you want any univector times your f of n become univector, then fn must be a unitary transform. Okay, so that's something you want to prove in homework, and I think that will be similar to this homework you want to prove. That's yeah. Because this thing is basically fn dagger. Okay, so basically you want to show fn dagger times f equal to identity matrix. Okay, and that should also be using this identity a lot. Okay, so you basically use this identity, then you show that fn dagger times fn equal to identity. So fn dagger also equals this thing. Fn dagger is fn minus 1. Okay. So that's a linear algebra on this fn matrix. It's a unitary matrix. Okay. Okay, so it's a unitary matrix, so we can think it as a quantum gate. Okay. So now we think this is as a quantum gate on n-dimensional quantum vector, so big n-dimensional quantum vector. And obviously we can just define a quantum gate this way. It's a unitary, so it's a valid quantum gate. Okay. And so just like before, we think we can write this as in components. So we are thinking we transform a vector in, so if it has standard basic coefficients, those aj from 0 to n minus 1, to another vector with amplitude in standard basis yk, k from 0 to n minus 1. And just as before, we have the yk should equal to this 1 over n sum over j, xj e to 2 pi over n times jk. Okay, so this is like writing this equation component-wise. Okay, and yeah, but this is pretty useful. Okay. And we can also think. Okay, so this is talking about component y. We can also think about component x. Okay, so we can define fn this way, but we can also define fn by column by column, right? So we can define what the fn do on every computational basis of x here. Okay? So we can write J will become yeah. So we can also think about what's the standard basis element got made by this Fn, and yeah, and it will be this thing. So 1 yeah. So it should be 1 and yeah, you can check this easy from here. So 1 e to the 2 pi jk over nk, and let's see some example here. So you can kind of see here. So if you have like j equal 2 here, and then you will pick out this component, this vector, and is a sum over all bases with phase e to the 2 pi jk divided by 4, and with like j equal to 1, so it's e to the, yeah, etc. Yeah, so it's e to the, it always has phase e to the 2 pi jk divided by n. And so J is the input J here, and the K is getting summed over. Okay? Any question about definition of quantum Fourier transform? So anyway, the definition is really here. So I guess you have a quadrant, you can always go back to the basic definition. Now, basic definition is you are multiply quantum Fourier transform is a unitary matrix, and it's a n by n big N by big N unitary matrix, and its jk's component is 1 over n e to the 2 pi jk divided by n. Okay. And once again, this is omega sub n to the jk power. Okay, and yeah. Okay, and if not, then we will go to show that we are a little short on time. But I guess we can start going this. Okay, so now we are going to show that quantum Fourier transform can be done really fast. Okay, and so we will give a pretty explicit circuit construction of it. Okay, and but for now we're going to restrict ourselves to qubits, yeah. Because it's more annoying it's harder to express this thing if n is arbitrary integer. Okay. So up to now, n was arbitrary positive integer, but yeah. But now we want to express things in terms of gates in qubits. So let's take a restriction of n. Now big N is 2 to the small n. Okay. So yeah, so it's 1, 2, 4, 8, 16, etc. Okay. So big N is 2 to the small n, and we are going to deal information in terms of qubits. Okay. And before we go to actual QFT circuit, we need to do some information. Okay. Do some notation. Sorry. And okay, and so now, okay, so you are seeing that we have all those things like J and K from 0 to n minus 1, and we want to identify those. So now we have this QB notation. We want to do everything in terms of n small n bit string. Okay. So we have a number from 0 to n minus 1. 0 to big N minus 1, we want to just write it as a small n bit string. And we have we have a very natural representation that's just you identify n bit string as a binary representation of some number. Okay. So we'll write J. Okay. So we think J is some number between 0 to big N minus 1, and equal to some small n bit string J1 to Jn. And that's just we thinking is J1 to Jn as binary numbers. So it means it's J1 times 2 to n minus 1 plus J2 times 2 to n minus 2 plus always plus etc. plus Jn times 1. Okay. And so for example, binary string 110 will equal to, so is J1 equal to 1, and so here we have J1 equal to 1, J2 equal to 2, J2 equal to 1, and J3 equal to 0, and also n equal to 3 here. Okay. So this is n equal to 3 string, and so it's 1 times 2 to the 2 plus 2 times 2 to the 1 plus 0. Okay. So it's 4 plus 2 plus 0, so equal to 6. Okay. So this is J1, J2, J3 equal to J. So J equal to 6 and J1, J2, J3 equal to 110. Okay. So this is just binary notation. Okay. So this PU should be very familiar. Okay. Now we talk about something that you might not be so familiar, that is represents numbers in binaries and represent numbers in binary but after the decimal number. But it's a binary, so I guess I should say call this after this binary point. Okay. So we want to define number that's 0.J1, J2 to Jn, and it's similar to this. Okay. So it's some number smaller than 1 but in binary. Okay. So after this 0 point something in binary, and that's just defined as 2, so it's just J1 divided by 2 plus J2 divided by 4 plus all the way to some Jm divided by 2 to the m. And for example, we have 0.11 will be, okay, so it's 0.J1 equal to 1 and J2 equal to 1. And it's 1 over 2, as we say here, plus 1 over 4, and it's 3 over 4. Okay? People okay with the binary rotation? So yeah, so we have those J1 to Jn notation and 0.J1 to Jm notation, etc. Okay. So if you are okay, then I don't think we have enough time. So maybe we'll start a little early. But anyway, let's see the claim here. Okay, so why we go over this restrict n to power of 2 and talking about the binary number, because we now have more, I guess, factored representation of QFT. So we're going to show what QFT do on computational basis state. Okay. So we have your input. Okay. So before we have this J to some over K, right? So now our J is input J state. So some computational base state, we can always write it as a NB string, small NB string. Okay. So we write this J as some small NB string J1 to Jn. Okay. And then we see that if we input is a computational base state, then very likely, I guess, output state is a product state. So it's a state is something on every qubit. Okay. And this something is 0 plus 1 to some weird phase. Okay. So we kind of do a bit of head mount on every bit, and then some extra phase. Okay. Okay. So we see that you have a computational base state, J1 to Jn, as the input to your QFT, and you apply input QFT on this, then you get this interesting product state. So first qubit will be 0 plus 1, with 1 having a phase 2 pi I 0.Jn. Okay. And remember, 0.Jn is this notation, 0.J1 to Jn. Okay. So this thing is so this is 0.Jn here in terms of decimal, and so this is either 0 or 1 over 2. So if Jn equal to 0 is 0, and Jn equal to 1 is 1 over 2. Okay. And so this phase, okay, so this whole phase together is 1 if Jn equal to 0, and it's minus 1 if Jn equal to 1. Okay. And yeah, so we have this interesting phase vector that depends on only Jn. And the second qubit become, okay, so we have essentially tensor product here. Usually tensor product. Okay. So first qubit becomes this superposition between 0 and 1. And second qubit is also superposition between 0 and 1. It's 0 plus 1 with now it's 2 pi times 0.jn minus 1 jn. Okay. And once again, this 0.jn minus 1 jn is this notation, and it's 0 point something something, and it's 1 over 4 thing, so it can be 0, 1 over 4, and 2 over 4, and 3 over 4. Okay. Okay. Etc. Depends on what your j minus 1 jn is. So 0, 1 over 4, 2 over 4, 3 over 4. And this thing is like 0, I, 1 minus I. Okay. And yeah, so every qubit you kind of see a trend here. So every qubit you get finer tuning on those phase here. So next one will still be 0 plus 1, but with the phase e to a 2 pi 0 point. So jn minus 2, jn minus 1, jn. Okay. So you have a 3 bit after the 0 point something number here, and etc. And all the way, okay, so all the way to the next qubit, it will be 0 plus 1, and with a phase of e to a 2 pi 0 point j1, j2, all the way to jn. And okay, so it is still a number between 0 and 1, but it's a quite long binary decimal number. Okay, and I get a binary fraction number. And we don't have time to talk about this in 3 minutes. Okay, so let's have a break early, but then next class we will, I can talk about this first though. Okay, and so this decomposition, although we are writing this as a quantum state, but it's a little digression, but you can write similarly. You can follow the split of this thing and write the decomposition for all those classical metrics too. And so this decomposition is actually pretty well known before people even doing quantum computation. And this is how you can do a so-called phase Fourier transform classically. But we'll see later that although phase Fourier transform is faster than how you doing Fourier transform naively, is still exponentially slower than quantum Fourier transform. Okay, so quantum Fourier transform is very fast, and it's based on this decomposition of Fourier transform. It's and in our world, is that you input the computational basis state to quantum Fourier transform, then you see the opposite state has this product state structure, so you can kind of fix every qubit to what it should be, and it's pretty fast. Okay, and let's have a 10-minute break, and then we'll prove this decomposition first. Then we'll construct our circuit for quantum Fourier transform. Okay, let's have a break. 方就是 algebra。
对，就等于说你真的要去看这个数是多少，然后再想转换一下，所以才会有那个4分之一、4分之2、4分之3，它是0.00到0.1。
现在那个几乎网和简约的，它都是算的，
对，
那应该是一算里面是这样子。
也就是 input 是一算0跟1。
对，然后它就放上去。
哦，然后再直接把这种东西拿来。
对，然后现在目前是讲说 click 的时候，我等下就会
get back. Okay. So yeah, so let's have a small recap today. So today we're starting talking about a very different concept. It's Fourier transform, and we have this 30 minutes introduction to classical Fourier transform. Okay. So we say classical Fourier transform is a way to, well, it's a matrix that let you transform an n-dimensional vector to another n-dimensional vector. And so intuitively, we think the n-dimensional vector as it's a discrete vector that that represents some signal in the time domain. And then the Fourier transform will tell you the frequency domain of that vector. And then there is an inverse Fourier transform to transform it back. Although our f and f inverse is kind of in reverse. But anyway, so kind of intuition is you want to see what your vector is in terms of those sinusoidal components with different frequency, or in terms of those complex exponential e to the I omega t, with omega getting bigger and bigger. Okay. And but based to mathematically, so mathematically the Fourier transform is this matrix with its kj's component, kj's element, e to the 1 over n, e to the 2 pi I jk divided by n. And so this very complicated e to the 2 pi I jk divided by n, you can think of this as omega n to the kj, where omega n is the nth root of 1. Okay. And anyway, then we see that this fn kj written in this way is actually a unitary matrix. So we can think maybe there is a kind of a quantum way to implement this fn, where we get a quantum gate that its effect is applying fn on some quantum vector. So now we think the input signal, we think about what if the input signal, this time domain signal, is actually a quantum state. Then we can get a quantum state correspond to the frequency domain signal. We get a frequency domain signal, we can get the time domain signal, okay, etc. So we want to find the unitary matrix fn such that you apply fn on x, it becomes y, and fn is, and x and y is related to this frequency domain and quantum time domain thing transformation. And so fn's jk element will be same as before, is e to the 2 pi jk divided by n times 1 over n, just like the classical discrete Fourier transform matrix. Because we are thinking this matrix is unitary, then we can think it as a quantum gate. Okay, so now we want to construct this fn efficiently through our basic quantum gates. Okay, and for now we restrict n to be 2 to n, so we can describe things in qubit. Okay. So big N was like the dimension of those matrices, and so now big N is the dimension of our quantum state, and we would like to think our quantum state in qubits. So let's assume big N as 2 to n, 2 to a small n, and so we are writing things in small n qubits. Okay. And first we do this binary notation. Okay. So now we want to count the bigger number. We can also just count the so count a bigger number. It can be count from 0 to n-1, but you can also express 0 to n-1 as a binary string. So a n-bit string can be correspond to some number between 0 to n-1 nicely like this. So j equal to some j1 to jn. So for example, this 110 string. This 110 binary string is the same as 6 in decimals. Okay. And then we have this more exotic notation where we say we can have a fractional binary string. Okay. So the 0 point something, 0 point binary string. So 0 point j1, j2, jn can be, and we say is j1 divided by 2 plus j2 divided by 4 plus all the way to jn divided by 2 to n. Okay. So we have a little more example here. So you have a 0 point just j1 and j2, then there are 4 possibility. So 0.11 in binary is 3 over 4 in decimal. Then you have 0.10 is 1/2 plus 0 is 1/2 in decimal, and 0.01 equal to 0 plus 1/4 equal to 1/4, and 0.00 is obviously just 0. Okay, so you see that if you have 2 bits, then you have those 4 possibilities. Okay, and so out of those binary notation, then so with the binary notation, then we want write our QFT in a very interesting expression. So we are saying if you have a computational based state into your QFT, so if your input state is a computational based state represented by J1 to Jn, so now you're seeing the J1 to Jn as this thing. So with the input state on J expressed as this J1 to Jn, then output state can also, obviously output state will depend on those J1 to Jn because the output state depends on J. But it has a very structured form, so it's a product between every qubit. So the first qubit will be 0 plus 1 with this 2e to a 2 pi 0.jn phase. And the 0.jn is this 0.j1j2 to jn notation. So this thing you can kind of think e to a 2 pi, so 2 pi, what do you know? But this 0.jn part is binary notation. Okay. So 0.jn can be 0 or 1 or 2, depending on jn. And then on the second qubit, we say the product with the first qubit is also 0 plus 1, but with this phase e to a 2 pi and 0.jn minus 1 jn. And also it's just 0.jn minus 1 jn. 0.jn minus 1 jn part is in the binary string notation. And so it has those 4 possibilities, and yeah, so depending on what jn minus 1 jn can be those 4 possibilities. And once again, remember this jn is from the input jn here, and this jn minus 1 jn here is from this jn minus 1 jn here. And anyway, so product with all those qubits and up to nth qubit, it becomes 0 plus e to a 2 pi 0.j1 j2 to jn. And once again, this part is in binary. Okay. And yeah, and then you have an overall normalizing vector. Okay, and now let's go to a proof. So why is this true? Okay. So proof start with our expression for Fourier transform. Okay. So we said before the J should become okay. So we start with this decimal notation. So J should become 1/2 to n, and summation over all possible k, and k from 0 to bigger minus 1, that's 2 to a small minus 1, and e to a 2 pi jk divided by big N, which is 2 to a small n. So now we are just writing big N instead of small n. Okay. Okay, so nothing really happened. We are copying, okay, let's scroll up. Remember, we are copying this expression. Okay, we're just copying this expression and say big N equal to 2 to the small n. Okay. And okay, and now we start to make things into binary string. Okay, make everything into binary string notation. So first we write k equal to binary string. Okay, so k is some binary. So this small k here can be written as some binary string. So because it's something from 0 to the minus 1, so you can write it as a small bit string. So some k1 to kn correspond to this k. Okay. Okay, and and then here we are summing all possible k, and obviously that's same as summing over. So every coordinate of this binary string is sum over 0 and 1. Okay, so here we have a 2 to n possibility, and we have a 2 possibility, and n of them. So this is also 2 to n possibility image. Okay. So you are summing all possible k, then that's the same as summing over all possible binary string k1 to kn here. Okay, okay. So this k becomes k1 to kn, and so this k up here is also k1 to kn. Okay, okay. But here we do something extra. Okay, so here we are saying, okay, so this k is maybe let's just write this down. Okay. So k is this k1 to kn string, but we kind of go back and forth, right? So we think k expresses k as k1 to kn string, but we want to express it back to, so this is binary, but we want to express it back to decimal, and so we are doing this thing here. Okay. So now this k number in terms of k1 to kn is k equal to, okay. Okay. And okay, so we want to deal with k and divide by 2 to n. Okay. So as k divided by 2 to n, so k divided by 2 to the n equal to, so this k thing itself, so maybe let's write this way. So 1 over 2 to the n times k1 times 2 to the, so k is also an b string, so 2 to the n minus 1 plus k2 times 2 to the n minus 2 plus plus kn times 1, right? So once again, it's this thing, okay? And now if you divide 2 to the n into this, then you see the k divided by 2 to the n, well, yeah, you divide 2 to the n into this, then you see the k1 times 2 to the minus 1 plus k2 times 2 to the minus 2 plus plus kn to 2 to the minus n, right? Just because, yeah, you see it measure up to this, because the 2 to n cancel with the 2 to n here, etc. And yeah, so you can actually write this in a more compact form. That is, you sum over, so there's 1 to n here, you can give another dumb variable L here. Okay, so this is 1 to small n. So you are seeing that you have a small n terms here for k1 to k small n. And so you sum over that with some small l here. So you sum over some small l from 1 to n, so you have kl. So kl for this k1, k2 to kn. And 2 to the minus l, because you see k1 paired with 2 to the minus 1, k2 paired with 2 to the minus 2. So l equal to 1 here, l equal to 2 here, all the way to l to the n here. Okay. Yeah. So you see that if we express a in terms of binary, then k divided by 2 to the n can be written as, so this is as the summation l kl times 2 to the minus l. Okay. So yeah, so second step, we break k into binary string, k1 to kl. But we kind of take the binary back to decimal, okay? It's a bit funny. And but anyway, this way we can write this in a nicer form, okay? And now we have the summation of terms on our exponent. Then we have well, you have an exponent of some summation, then is a product of every individual terms, right? So instead of sum over L here, we can have a product over L here. Okay. So yeah, so we can have a product of e to the 2 pi I k o to L, and multiplying over L. And we also do something. So we also think, so is k1 to kn. Okay. Yeah, and so now we also do something extra. Okay, so here we will kind of just mathematically write k in terms of k1 to kn, but now we also remember we are having those things as a bit string, right? So this k1 to kn is actually, so it's a computational basis there, and it's actually the first bit in k1 tensor, second bit in k2. Tensor the nth bit in kn, right? And yeah, so now you think you have the factor here as the product of factors, right? So the first one depends on k1, and the second one depends on k2, the third one depends on k3, etc. And so you can just because the tensor product, and you can have the multiplication factor everywhere. So we can just group this k1 vector with this k1 here, then tensor the k2 vector with this k2 here, and put all the way to the kn vector with kn here, right? So it's this thing. Okay. So L equal to 1, you have the e to the 2 pi k1 e to the minus 1, and you can put it together with k1 here. And second term, you have the e to the 2 pi k2 to the minus 2, then you can put together with k2, etc. So you have actually a tensor product with all those terms with KL. Okay. So L from 1 to n. So you have small n terms as a tensor product with each other. With the phase vector only depend on KL, and then you have this one bit depend on KL. Okay. So K1, K2 to Kn. And here K1, K2 to Kn. Okay. The vector as we have here is e to the 2 pi j and the KL 2 to the minus L. Okay. Okay, and yeah, so now we see we are kind of in our product qubit form. Now we have a product of every qubit, product of qubit with some vector here. Okay, and so the next thing we do is we can put the summation inside in this tensor product, because we see that okay, so the KL with K1, so we see we have turns as product of those things only depend on K1, things only depend on K2, and things only depend on Kn. And we also have those summation of different K, right? So the summation of K1 to Kn. And so we can put the summation to each of K. Okay. So we can have the summation of K1 together with K1, and the summation of K2 together with K2, and summation with Kn together with Kn. Okay. And so we write in this way, then so you put all those summation inside, and it's just summation of KL from 0 to 1. Okay. So instead of writing our n summation here, then you put this summation inside, and it's just for every L you sum KL from 0 to 1. But there are n over L is from 1 to n, and so there is basically still n summations. Okay. So put the summation inside, and because every KO is all grouped together here. Okay. So you can just put the summation inside this product. Okay. And so now we are basically done. Okay. So we have a product of every qubit in terms of some summation. So if you actually write down this summation, okay, so each KO is summation between 0 and 1. Okay, so now you put the KO equal to 0 to 1 here. If KO equal to 0, then well this is 0. And this vector here will be 0 because you have a 0 here, then this whole thing becomes 0. Okay. And the e to a 0 is 1. So you have a 0 here, and the K equal to 1 means this qubit is in 1. Okay. And it's 1, and the thing up here is, well, it's 1 here, but you see the other thing, you have e to a 2 pi j 2 to the minus L. Okay, so here we are just writing all this summation of KO equal to 0 and 1. Okay, and so we are basically done here. Okay. So the next thing we need to do is we need to figure out what is e to a 2 pi I. Okay, so e to a 2 pi are all universal constant, and every only interesting thing here is j 2 to the minus L. Okay. So now it's time to remember what is j. J is our input. Okay. Remember we are saying j. We have some j from 0 to a big N minus 1, and it will become this state. Okay. So we break k equal to the binary and got all the way here. And now we are going to break j equal to binary 2. Okay. Remember, our thing has a j in binary, so obviously we want j in binary. But before we didn't need that, so we have a j in decimal up to now. Okay, so now we break j to binary. Okay. J in binary is j1, j2 to jn. Okay. And we are going to have j divided by j times 2 to the minus L. Okay. So it's going to be j divided by 2 to divided by 2 or j divided by 4, etc. And what are all those numbers? So j is j1 to jn. And now you think about the decimal, you think about the binary operation. And if you divide j by 2, then it basically shifts this binary point by 1 slot, right? Yeah. This you can verify yourself very quickly, so I won't write the proof. So if you divide j by 2, then you move the decimal point, or really binary point, by 1 slot here. So instead of j1 to jn, you have j1 to jn minus 1 dot jn. And if you divide by 4, then you move this point 1 more, okay, etc. Okay, and okay, so that's what is j times 2 to the minus l should look like in terms of binary string of j. It's j1 to j something point, then all the way to jn. Okay. And but what it really is, if you include this e to the 2 pi, then you see that everything before decimal point is useless. Okay. So for example, you have L equal to 1 here, right? So for L equal to 1, you have j times 1 over 2 is j1 dot 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 jn minus 1 to and the point jn. Okay, so this is binary string. And you think e to the 2 pi is binary string. And so you have an integer part here, and then point the decimal. But the integer part doesn't do anything, because e to the 2 pi equal to 1. So that means e to the 2 pi, e to the 2 pi times any number, and the integer is still equal to 1. Okay. So yeah, so integer part times the e to the 2 pi just does nothing. So actually, this L equal to 1 term, the only thing matter is this 0.jn. Okay. And yeah, so your first term become e to the 2 pi 0.jn. And your second term will be e to the 2 pi 0. So second term is this thing, L equal to 2. And you'll see that you divide by another 2, so e to the minus 2L. So divide by another 2, and then you will pull j minus 1 over your decimal point. And so you will have 0.j minus 1 j here. And so you see that when it will get bigger and bigger, you divide j more and more, and then you pull more and more bit over this binary point. And so you get all those binary fraction. So 0.j minus 1, and all the way to when L equal to n, small n, then you pull every bit of j over this binary point. So you get 0.j1, j2 to jn. Okay. So these are in binary. And yeah, so that completes the proof. So we see that if you have j that corresponds to some j1 to jn, and go through QFT, and it should become this product state. Okay. So 0 plus factor to 1, 0 plus factor to 1 with 1, and 0 plus factor with 1. Okay. So any question about this QFT decomposition of QFT? If not, then we can finally get to our QFT circuit. Okay, so you see this is a product state, and what we really need to do is want to turn every qubit into those form. Okay. And yeah, so this is a circuit to do it. So you think input state is J1, J2 to Jn, as we say, and then we'll apply headman on everything, and because everything is at 0 plus 1, and then we will write the factor, try to control the phase onto it. Okay, and so to get those 0 point j something factor, we define some rotation matrix that's nice. Okay, so just define a rotation matrix. Okay, so it's actually a 1 cubic gate. So we define this rotation matrix is this diagonal matrix of 1 and e to the 2 pi I divided by 2 to the k. So it's like rotating exponential small rotation. Okay, so you get HI e to the 2 pi divided by 2 to the k vector onto your 1. You can kind of see that. So this will change the k speed here, right? Okay, so what do we do? So what we do is we rotate the first qubit into this thing. Okay, so first we make it into actually 0. So it will become 0 plus e to the 2 pi 0.j1 with this hedema. And then with this R2, we'll add this J2 here. So we control on this J2 and do R2 here, and you will add this J2 here. And so all the way, then we do control R3 and we'll add J3 here, and all the way to we control on Jn to do Rn, so we will add Jn here. And so we will bring the first qubit into the last qubit here. Okay. And then similarly on second qubit we do hedema and we do more control, etc. all the way. And all the way to the second last qubit, we do hedema and we do hedema to make it into 2. Okay, so it's Jn-1. So we do hedema, it will become e to the 2 pi 0.Jn-1. And we control R2 on Jn, and it will become this 0, and you will add this Jn here. And then finally we can make a hedema on the last qubit, and it will become this thing. Okay, and so we see that applying this circuit, this hedema control hedema control this circuit, and the end result is what we want. 3 example. Okay, so we have a small example that can write out everything. And okay, so our formula says that if applied this 8-dimensional Fourier transform on our J1, J2, J3, it should become 1 over square root 2 of this 0 plus 1 with e to the 2 pi 0.J3 and on first qubit, and e to the 2 pi 0.J2, J3 on second qubit, and e to the 2 pi 0.J1, J2, J3 on the third qubit. Okay, so it's all 0 plus 1, but with these weird faces, and also 1 over square root 2. Okay, and we say this circuit will make J1, J2, and J3 exactly into those 3 product state. The product state of those 3 things. So this product should give you this, and this product should give you this, and this product should give you this. Okay, and okay, and I guess our verification is not quite complete, but so we start with we see what's the H on J. Okay, so hedema on J will give you 1 over 2 and 0 plus minus 1 to the J1. Right. This is hedema. Okay. Because hedema I always give 1 square root 2, and it's 0 plus 1 or 0 minus 1, and it's 0 minus 1 if J equal to 1. So it's minus 1 to the J here. Okay. And then you see the minus 1 to the J is e to the 2 pi 0.J. You can verify this is quite true. I guess it's because minus 1 is e to the 2 pi divided by 2. So minus 1 to the J is e to the 2 pi I divided by 2 times J. So it's e to the 2 pi I times J divided by 2, and J divided by 2 in binary is 0.J. Okay, and I guess let's verify the first qubit. Okay, and so H on J1. So H on J1 you will become 1 by square root 2, 0 plus e to the 2 pi I, 0.J1, and then you do this Control R2, right? Then you do Control R2 on J2, and oh, I'm missing one here. Okay. And then this thing we say is become 1 over square root 2, 0 plus e to the 2 pi I 0.j1, j2, 1. And this is because when j2 equal to 0, then you don't do this control R2. So this thing, so j2 equals 0, then this is same as this because then this number equals this. And when j2 equal to, okay, then j2 equal to 1, then you add the extra phase on the phase on the 1 register, right? Because remember our RK look like this. So when j2 equal to 1, then you add e to the 2 pi I divided by 2 squared. So you are adding basic. And so I guess we should write this in binary, right? So sorry, we write this in binary. This is 1, 0, 0, and e to the 2 pi I 0.0001, and this is a case bit. So this is a case bit after this point. Okay. So if for example k equal to 2, then k equal to 2, then that is ready here. So k equal to 2, then R2 equal to 1, 0, 0 e to the 2 pi I divided by 4, and it's equal to 1, 0, 0 e to the 2 pi I, and 1 over 4 is like 0.01 in binary. Okay, so we kind of have the binary in underscore. Okay, and yeah. And so you see that if j2 equal to 1, then you add 0.01 here, and as you see, so that's exactly what they do here. And then finally, then you do Control R3, and you will add on the circuit bit, and it become. So I should not write the equal sign here. And you control R3, then it become 1 over square root 2, 0, and then plus e to the 2 pi I, 0.j1, j2, j3, and this part in binary and 1. Okay. And yeah, so once again, it's the same idea. So j3 equal to 0, then you don't add anything. And j3 equal to 1, you add 0.001 in binary onto this face. Okay, and yeah, so this small calculation shows that is H1, H, Control R2, Control R3 turn the first qubit into this qubit here, and similarly HR2 will turn things into this, because H give you this 0.J2 and this R2 give you this 0.0J3, and finally this H turn this qubit into 0.J3. And as we say, that's a reverse order of those 3 qubits, because we want this order as this. So we want this order, but actually we have this on first, and this on second, and this on last. And so we reverse the ordering by doing the swap gate here. Okay, so that's an example of n equal to 3. And为什么反设计？因为没办法直接转啊，就是J1，我想想看啊，反折设计是基本上应该是没有办法直接转吧。我想想看，你是想要直接把第一个 qubit 转这个东西对吧？ 我觉得非常的困难。我觉得可以吗？我想想看，你要把第一个 qubit 转这个东西，可是这样的话其实不太行，因为怎么说呢？如果你先看看你要什么顺序嘛，我们可以想一下。第一个 qubit 你先转这个东西的话，那一定是不行的，因为这个转完了，你会发现我们这里做完，我第一个 qubit 把它转完这个东西之后，我可以这样子做，是因为这个做完了，我就不需要 J1 了，对吧？我把 J1 变成这个东西之后，但是你会发现这里面跟 J1 有关的只有在这里，对吧？先说这里为什么可以这样做啊？对，这里可以这样做是 OK，sorry, I should back to English. Okay, yeah. So the question is, why do we need to do this reverse ordering? Can we just have this in the correct ordering at the beginning? Okay, and I guess that's say a little bit why we want reverse ordering, because we are actually using some nice property here. So we want to make the first qubit equal to, so we want to make the first qubit equal to this thing, because if you look at this thing and you see the only depends on J1 is here. Okay, so if you turn equal J1 to this complicated thing, then you don't need to know J1 anymore. Okay, so you can turn J1 equal to this thing, and so see on those parts you don't really touch J2 and Z3 because you are only doing control on it. Okay, so you turn J1 equal to this weird thing, and so basically you forgot what J1 is. But that's okay because all those things doesn't depend on J1, and J2 and J3 are still intact, and then you can turn J2 equal to this thing because so you have J2 here. Okay, so you use J2 on those two things. Okay, and then you turn J2 equal to this thing, and then that's okay because the last thing only depends on J3. You don't have to depend on J2 here. And yeah, so if you reverse ordering, I think it will be very hard because, say if you want to turn J1 equal to this first, then you lose the information on J1 and it's hard to do the last thing. And say if you want to turn J3 on, so if you want to turn J3 to this first, and it's still weird, yeah, right? Turn J3 equal to this thing first, then you still ask, can you? Yeah, if you turn J3 equal to this first, then it's hard to access J3 up here. But maybe you can. I guess a lot of things commute here. So, maybe there's a way. I cannot give a really rigorous proof here, but it seems very hard to me. Yeah. Maybe there's a way. If you do the control carefully. So I guess you can do the hit mark together at the beginning, right? And yeah, I don't know. Seems hard. You can try it, but remember here we are using this. Here we are using the property that you turn J1 to this qubit, then you don't need J1 anymore, so you can do all the other calculation nicely. Okay. Yeah. So, and if you want to get rid of the swap gates, then you need to take care of your information carefully. Remember that you rotate something, then you don't really get to do the classical information on it anymore. Okay. So it can be hard. Okay. Any other question? If not, yeah. If not, then so I guess Then we have proof of those in all numbers. Once again, I'm not sure this is too informative, but I guess we only have 10 minutes, so let's try to go through this. Okay, so we have a more general proof, but really it's the same idea, but with more complicated notation here. So we have one input J1 to Jn, and we say we hit them on first qubit, and it becomes 1/square root 2, and the first qubit becomes the superposition between 0 and 1, and it turns J1 to 0.J1. Okay, and this is the thing we can hear. Okay, so you apply Hedema on some qubit, it's just e to a 2, just 0 plus 1 with e to a 2 pi 0 j on the qubit. Okay, and yeah, so you apply Hedema on first qubit, you become this 0 plus 1 on first qubit with 0.J1, and control R2 will add 0.J2 here, and control R3 will add 0.J3 here, and you do all the way to control Rn, and you will get 0.J1 to Jn on first qubit. Okay, and here you can kind of see a little more clearly. So you see that you turn first qubit into this complicated thing, but J2 to Jn is still in the computational basis state. And yeah, so you can kind of see it here. So you do all those things on J1, but so up until this point, J2 and J3 are still in computational basis state, because you only get those control gate from that, and we think you input as a computational basis state, so you are just reading J2 and J3 from that. Okay, so you turn J1, so you turn first qubit into this complicated thing, and the other thing is still in computational basis state, and the other computation you want to do doesn't depend on J1 anymore, so it's okay that you kind of lose information on J1 here. Okay, and yeah, so you do similar thing on second qubit. So you turn J2, so Hedema turn J2 equal to this 0.J2, and then control R2 get you 0.J2, J3, and all the way to control N minus 1, control Rn minus 1, and that will give you this Jn here. Okay, so you will turn the second qubit into this thing we want, and now J3 to Jn is still in computational basis state. Okay, and the other thing you want to do doesn't depend on J2 anymore. Okay, so continue all the way through, then you get this the state we kind of want, but with a reverse order, and we reverse order with a whole bunch of swap gate, so we get the state. That's quantum Fourier transform proof. Okay, so yeah, so once again, this is the circuit for quantum Fourier transform. Is Hedema, whole bunch of control, Hedema, so Hedema, and N-1 control, then Hedema, and N-2 control, all the way to Hedema, 1 control, and Hedema. So a whole bunch of Hedema control, then there is a reverse ordering. That's the quantum Fourier transform circuit. Okay, and finally, let's see how fast this is. Okay, so how many gates do we have? Okay. We have order n square control rotation, because it's like n plus n minus 1 plus n minus 2 all the way to plus 1. Okay, or I guess control rotation and Hedema plus Hedema. Okay, I guess that's control rotation. Hedema. Okay, Hedema is like a control rotation, but technically not. Plus Hedema. Okay, and okay, so you whole bunch of control rotation Hedema order n square, small n square, plus and there is some swap gate at the end, and as we see, you can basically just swap these by pairs, right? So the first one with less one, and the second one with the second less one, etc. But anyway. So that's like n over 2, but in terms of big O, that's order n swap gate. And so the total number of gate is like order n square. Okay. So okay, so we are cheating a little bit because control rotation are not like in our universal case set, but let's just assume it's close enough. Okay. Yeah, I think it's actually not too different. Yeah. Yeah, we are cheating a little bit. So you can, I guess, as a good question to check yourself is how much gate you need to do on the control rotation. Okay. But anyway, so we have about order small and square gates. Okay. And so now we back to big N, and that's log square big N. Remember, big N equal to 2 to n. Okay. So this is how many gates we need to use to do quantum Fourier transform. And now compare to classical Fourier transform, and let's just state a factor fixed here. Okay. So classical Fourier transform, you want to get some vector v, and you want to compute the fn of v. Okay. And so with a similar decomposition, how many operations you need to do is about theta, big N, log n. And so you need to do those many multiplication and addition with the so-called phase Fourier transform. Okay. And this is already phase using a similar decomposition we have. So if you think about if you just do brute force matrix multiplication, so you have an n by n matrix times an n-dimensional vector, then each coordinate you need to do like inner product with n-dimensional vector, so that's like n multiplication addition, and there are n of them, so it's order n squared, right? Okay, so if you do this in stupid way, it's order n squared, and if you do it smartly, then it's order n log n. Okay. But anyway, compared to quantum Fourier transform, it's much slower because the quantum Fourier transform only order the log square n. And yeah, so it's an exponential improvement over classical Fourier transform. Okay, but here is a little catch here. Okay. So the little catch here is, remember the input-output state quantum state. Okay. So you cannot really use quantum Fourier transform to do classical Fourier transform. So like you have some data, and some data you know want to do Fourier transform it, and so some classical data you want to do Fourier transform it, and now I think we have quantum Fourier transform algorithm. Maybe can we do this really fast with a quantum computer? And the answer is not quite, because you need to turn those data into some quantum states. And okay, so assuming this step is okay, but even though then you can do quantum Fourier transform really fast, then you get some state y, that's the quantum Fourier transform x. But now how do you get the y equal to the classical data? It's actually very hard, right? Because you have so now we think that n is very large, and you have really large, you have a bigger dimensional quantum state y, and you want to learn its all of its amplitude to get back to your classical vector, and you can prove that it's actually very hard. You need like at least order n number of calculation to get your data out. Actually, you need many copies of y to get this out. Okay, so yeah, so you cannot really quite use quantum Fourier transform to do the classical signal processing Fourier transform for you. Okay, but it's still useful as a part of our quantum algorithm, and as we will see in a few weeks, that quantum Fourier transform let us do factoring. But okay, so it's exactly on time, but a little spoiler, before we do factoring, we will actually talk about more basic element of it is we are going to use quantum Fourier transform to do phase estimation. It's actually still pretty quantum primitive. Okay, so see you next Tuesday.